chair's getting in the way. Okay. Hello, everyone. Welcome to another Learning Glass session. Today, we're going to talk about second law, which has to do with entropy, which has to do with real processes, which is pretty much a big constraint in designing and analyzing systems. Does it violate the laws of thermodynamics? And most of the time, that means if we apply the second law, does it violate this law or not? And if so, how can we minimize the effects of the second law of thermodynamics? So when we apply these laws of thermodynamics, we have to define a system, such as this blob here. What's inside of here is what we're concerned about. This is our system, and we defined it by drawing a boundary, of course. And that means everything else is the surroundings. So we apply analysis on this, and there's interaction with the surroundings through the boundaries. So if we were to draw the state of the system in terms of entropy and temperature, so this is the temperature of your system, the entropy of the system. If we were to start off at a certain state 1, this applies to a process, and one example to think about how important this is that even if you were to design a process where you were to go across many different states, but then come back to your same initial state, such that state 1 equals state 2. So this is the system state. Even in that case, so it is possible to carry out a process or cycle. This is a cycle in that case. With the state initial equals the state at the final, the final state is the same, such that, of course, that means delta equals 0. There's no change. So you can do that, but the important thing in terms of a real versus a theoretical limit that we're going to analyze is that you can have a reversible process only if this condition applies. So reversible, thermodynamically reversible, meaning like some theoretical limit that we're going to use as a useful guide in terms of the theory, is that reversible process only applies, you're only reversible only if and only if, that's what this two F's means, their change in the state of the system equals 0, and the change in state of the surroundings equals 0. So both of them have to apply. So what makes an irreversible process is pretty much what happens in real life. You can have a cycle where the state is the same at the beginning, you come back to the original state, and so delta S equals 0, but delta S of the surroundings does not equal 0. So that's the essence of the second law of thermodynamics, entropy, and what happens in real life is that you can design an engineering device, or you can have a process where you start off at one temperature and pressure and internal energy, for example. You undergo many different states and you come back to the original state. And in that case, that the delta, the change in state is 0. And in real life, you have some effect on the surroundings, and it's impossible for the surroundings to go back how they were beforehand. That's a pretty precise way to describe an irreversible process. And we're going to use the laws of the thermodynamics to quantify that. And a theoretical limit, which we'll talk a lot about in this class, is, it doesn't happen in real life, but it's a theoretical limit, is that you can do a process where you go back to the original state and somehow the surroundings go back to the original state. So one way, a good way how all of this got formulated mathematically was by the Clausius inequality. There's two S's, I don't know. Double check that. Clausius inequality, which is a corollary, like it's a part of the second law. What it says is that if you were to look at some cycle like this, where you took the heat transfer across all the different stages, this differential heat transfer, divided by the temperature at which the boundary, the boundary temperature where this heat transfer occurs, you always have to have a value less than 0 across this whole cycle. So this means this integral is a path integral. This circle means a path integral. This arrow means you're across the whole cycle. So this is the integral over the cycle such that S1 equals S2. And this is the boundary temperature. So it's heat transfer across this boundary. This is the heat transfer along the path of the processes you're taking. And of course, the amount depends on path, as with all heat processes. So all of this, if you apply integral over this process, you have to have something less or equal to 0. Okay? That's just something that popped out of all of these experimental observations when we're trying to build heat engines. So let's talk a little bit more about this. It's something, it's one of the ways where you say, oh, did you violate the second law of thermodynamics? No one has ever shown that they can overcome this limitation. If you apply this cycle to a heat engine, which is a set of series of processes, and they occur in a cycle where the initial state equals a final state at one point, and that's how heat engines work. You keep on pumping a cylinder up and down with this burning of fuel. You get mechanical work out from this high temperature working fluid, and if you're going in a cycle, you're limited by this Clausius inequality. It's one of the ways of describing, quantifying the second law of thermodynamics. So another way to think about it is, if you do this integral again over the cycle, this integral, another way to write this inequality is you say that this integral plus some amount of the cycle equals 0. And then you can make this criteria for values. There's different conditions. So if you have this turns out to be greater than 0, then it's irreversible, which is real. If you have this equal to 0, then this is reversible. Possible, but it's a theoretical limit. And if you have this value less than 0, that's where this inequality applies. It's impossible. You violated the second law of thermodynamics because this Clausius inequality became greater than 0. You violated this inequality. And this is one thing to realize is that this applies here. Even though state 1 equals state 2, you still have some, spoiler alert, what we'll call this is you're generating entropy. You're having an effect on the universe. You're generating entropy, and it's impossible not to do this in a real process, and it's equal to, it's impossible to decrease the entropy. You're either going to not have an effect, which is not real, but it's a good theoretical limit to understand. And in any real process, you're going to have some finite amount of entropy generated. So this applies even if the state 1 equals state 2. So if you go around a cycle, you don't do anything to the system at any net result of the system, you're still going to have an effect on the universe, which is given by this Clausius inequality. So you have to have another way of saying this is that this has to be greater than or equal to 0. And for any real cycle, you'll have something greater than 0. Okay, so let's write more stuff. Yeah, I can erase this because it's over here. So the Clausius inequality is there. It's related to heat transfer. It's a direct relation to heat transfer, but even if you don't have heat transfer in a direct part of the process, you can still have friction, which is related, of course, but you can describe it in terms of some entropy generation due to friction, due to an irreversibility in your system, which we know friction would be one of them. Okay, so now that's one way to define entropy. Entropy, it's a state variable. One way to think about it, it's a state variable quantifying second law. So it's a way of describing the second law, and the first law tells you that you can you're not destroying or creating energy. You are transferring energy between the states of the energy levels of the system and energy transfer coming in and out. That's the first law. The second law is saying that even if you do any of these processes, you're going to have an effect on the universe, which we're not there yet, but that effect of the universe is you're going to have less and less energy available. That when you do something, it's going to create entropy, which makes less and less mechanical work available for your needs in terms of engineering applications. So if we define entropy, we can use the Clausius inequality saying that one way to define entropy is saying that if you have a process going from state 1 to state 2, this is S, entropy state at the end minus the entropy at the beginning for a process equals an integral from state 1 to state 2 of some integral differential heat transfer, and it's only equal if this process is reversible. That's one way to define entropy. And where the entropy generation, this sigma term here, then becomes entropy generation. And it also applies to this Clausius inequality. So one note about this is that it's a state variable. So if you have a process with the same endpoints in terms of the temperature and other state variables, the change in the entropy, it doesn't matter whether it's irreversible or not in terms of this change. Because, or I'll say if state 1 reversible equals state 2 reversible, state 1 irreversible, sorry about this. I'm not talking about a cycle anymore. I'm saying if we're comparing two different processes, one is reversible, one is not, one is irreversible, but you have them starting and ending at the same state, you'll get the same entropy change. But you could only use this equation if it's a reversible process. So if you know the state variables, you can use those, or you can use tables. If you know that the heat transfer occurs reversibly, then you can use this equation. And another I'll write down on how you get entropy would be something like this. How do you quantify it? But then so to find entropy, you use a reversible heat transfer. You need Q reversible or state variables directly or table of states, which is the same thing as state variables, but this is like in an equation. You know, given this, you can use different equations that we're going to talk about in class, not today, but in class. Okay. So that's a good point to erase. So like I said, it's a state, entropy is a state variable. It's related to the second law of thermodynamics. The second law of thermodynamics tells you that it gives you another constraint on real processes versus impossible processes. In any real process, you're going to generate entropy to meet the Clausius inequalities constraint. And that occurs for any process. I mean, it doesn't have to be a cycle anymore. We kind of skipped some steps, but this applies for any state going from one state to the other, state 1 to state 2. Doesn't have to be a cycle. But because entropy is a state variable, if you know the state variables at the beginning and you know the state variables at the end, you could always find entropy change with some equations we will develop in the course. So that's good. And it's harder to use this heat transfer to find entropy because in any real process, the heat transfer is never reversible. So you have to use state variables. And if we may remember from steam tables from last semester, the steam tables are built upon the state postulate, which says that if you have two independent variables, you can define the whole system. And that's one way to find entropy. You can say if I know two other state variables, then I know the entropy has to be this if I have a table of all the thermodynamic properties of this system. And there's a lot of ways to do that. Okay, I'll go ahead and resolve this. And similar to energy balance, we're going to apply balances to entropy to say that to help keep track of and quantify the entropy in a process. Okay, let's do that. So, closed system entropy balance during a process and a system. So the system is undergoing a change of state due to a process. And if you have a closed system, you can write that the entropy change is balanced by it's due to some heat transfer, and you integrate that over state 1 to state 2. It's a heat transfer at a given temperature at the boundary, plus, so this doesn't have to be reversible anymore. If it's any real process, you define this other kind of balance. You know that some entropy has to be generated in the system. So your system has a entropy 1 and entropy 2. That's what this entropy change is keeping track of. Even if the heat transfer is not reversible, you quantify this amount, but you have this other unknown, this entropy generation of your system. So this balance is only completed when you add this extra term here, which is an unknown to be solved. So this is the system entropy change. This is heat transfer through a boundary with the temperature T. And this is entropy production. So this is the entropy generated within the system. Okay? So some constraints on this is that this difference, it can be greater than 0, it can be equal to 0, and it can be less than 0. So it can take any value depending on this balance here. Similarly with this heat transfer term, the integral from 1 to 2 of this heat transfer over the temperature could be greater than 0, could be equal to 0, and can be less than 0. So it can take on depending on which direction the heat transfer goes. Heat in, heat out. So if there's no heat transfer, then there's less entropy generated, but that only means that you won't have any entropy generated due to heat transfer, but you can also use this term to kind of quantify friction or other irreversibilities that are not directly due to heat transfer. A lot of them are, but not, you don't have to. And this entropy generation term, draw it more. System, it can be greater than 0, it can be equal to 0, but it cannot be less than 0. So if it's greater than 0, then it's irreversible. Which is a real process. If it's equal to 0, then it's reversible, which is a theoretical limit. It's the limit. Doesn't actually happen in real life, but it's a very useful concept to understand. And if it's less than 0, you violated the second law of thermodynamics. Violate second law. Okay. So now, let's do this balance for an open system. Open system, you can say that this system might have mass coming in and out. So there can be some accumulation or depletion with time depending on the mass balance. And you can have multiple inlets and outlets where heat transfer occurs, or multiple surfaces, boundaries, where heat transfer occurs. So across all those boundaries, there can be some entropy change due to heat transfer. Then you would sum up all the inlets and outlets and say that there's some mass flow in with a given entropy in minus what's coming out plus, because this is a flowing system, you have some entropy, a rate of entropy generation. Don't forget that one. Okay, so that's the balance. This will be accumulation or depletion due to mass balance. So if the mass is steady state, then you won't have any of this accumulation or depletion. Each boundary heat transfer location. If you draw a big blob, you might you can quantify the entropy contribution across different areas with different temperatures. This is the inflow. This is outflow. The mass flow rate of a given inlet or outlet times the entropy at that location, that source, in or out. This is the rate of entropy generation of the system. System. Supposed to just say system. So that's the balance. And one thing is that if you don't have any accumulation or depletion of mass, this dt term goes to 0. Depends on the mass balance. Okay, so these are a couple of cases. A closed system, the entropy balance would look like this. An open system, entropy balance would look like this. Let's do an example of an actual device